Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Hi, welcome to Speaking of Reliability. This is Fred Schenkleberg.
And this is Chris Jackson. And what are we talking about today, Fred?
Well, I got a question, actually. We ask for it just about every time. I got one, and reaching out to you to ask for advice regarding the effect of electrical or mechanical components, which immediately made me think this is a very broad question, due to excessive starts and stops. The first thing I thought of was this bus driver that used the accelerator to the floor and then the brake to the floor. And I think that would qualify as excessive starts and stops. But it was like a toggle switch. I think they would have saved a whole lot of the design if they just gave this guy a toggle switch, full on, full off. So the question is how can this be modeled, or how can we calculate the effect of the component failure rate? And do you have any experience in this, or know of a paper or something like that? And I suspect one of the first things we're going to talk about is there's not a generic conversion of power up, power down, or start or stop, or how long it'll last, or how well it models, or whatever. Because every component, every set of designs, every mechanical system has probably one or more failure mechanisms that are most affected by starting and stopping. And then I was like, what do you mean by excessive starting and stopping? Is it more stress, more damaging stress of a different kind than what you get under normal start-stop scenarios, normal cycles? Or is it the same mechanism, but it just happens faster? Is this an accelerated test question? Is this a design question? Is this a use condition type thing? So I answered, I think, with 3 different scenarios of how to approach that question after saying electrical or mechanical components. Well, that's pretty darn broad in the range of failure mechanisms that can be affected by starting and stopping, or turning on or turning off. So I thought I didn't get more information back yet, so I'm kind of blind as to the details of this one.
Well, the issue is that it's a different failure mechanism, or involves different failure mechanisms. So when you're testing for, let's just say, throttle open conditions, you're stressing your system in a particular way. Mm-hmm. When it's starting and stopping, you start stressing it in a different way. So it's going to be a whole range of different failure mechanisms. So if your test focuses on just throttle open conditions, then it's not going to be including in its test scenarios or stresses the stress. I'm using English not good right now. When it's,
I'm having an influence on you. Yeah. My old English teacher in 6th grade would be so proud.
Well, what am I trying to say here, Fred? I'm trying to say that if you just test when the throttle is open, so to speak, then you're just simply ignoring or avoiding or discounting the stresses that your thing experiences from being turned on and off. You're just not testing for it. You're not looking for it. So,
well, a real example of that is the aircraft industry. They evaluate takeoff because that's a particular set of loads and stresses on their aircraft. And then they do in-flight, which is a whole different scenario of loads and stresses and conditions and temperatures and everything else. And then they test landings. And I think it's pretty obvious why in all those cases. And then I got a question from a company that made the brakes for aircraft. And they were trying to quantify flight length on how long their brakes would last. I says, it doesn't matter where it flies 3 miles or 3,000 miles. The brakes are not in use. What is the failure? What is the stress while the brakes are parked under the fuselage? And they might be energized. Maybe there's a little bit of that, or maybe it's thermal cycling that's a factor in this. What exactly is it you're worried about that a long haul flight will damage your brakes? And they couldn't answer that. And says, well, then you got nothing. If your thing's so robust that can survive landings and takeoffs and taxiing in every environment around the world, I think flying inertly is kind of the least of your worries. But they were saying, but we do know that if you fly long flights, you don't use the brakes as often. Says, yeah, that's true. And we're trying to create a correlation that way, that how long their brakes last if you only flew long distances. This is like your car on a freeway. If you drive great distances every day in a nice, clean, clear, easy drive, yeah, your brakes are just not put to the test. There might be some vibration, right? What what do you mean by start stops and excessive? That was my first term I picked up on, is what do you mean by excessive start stops? It's like really, really hard start stops. Like we were talking in the last episode about battery charge discharge. You know, you do fast discharge, fast recharge, which is more stressful on a battery. Or do you mean that they do it a lot, say a taxi versus a personal automobile? And like, I don't, you got to be more clear in the question. I like the question. I like getting questions like this, but I really sometimes wish I had more detail.
But I suppose the question now, if we were to go back to the only way I'd be able to come up with a number if it was put in front of me was if you had testing that was able to characterize throttle open conditions and the reliability or the failure rate at those conditions. And then if you had a separate test or so separate analysis or separate understanding of the amount of damage each turn on, turn off thing cycle creates, the number of turn on, turn off cycles to failure, so to speak. That's two separate models that you could hypothetically model as under an OR gate and a fault tree or as a series system, i.e. the system will fail when one of those two failure scenarios causes failure. Then I would need to have a mission profile or a usage profile, which says that for every 300 hours used, or 300 calendar hours, it's used throttle open conditions 150 hours, and it's turned off and on 6 times.
Yeah.
The
sets of profiles would be even better. But I get that. It's the and it goes back to here, unlike our last episode, we'll talk about failure mechanisms much, much sooner in this one. It start with, well, what's this, because when I was working with mostly electronics, when I was working at Hewlett Packard, one of the big concerns we had with most electronic boxes that we dealt with was when you turn on the power, there's an inrush current. And if you don't account for that inrush current, you can inadvertently create a pretty nasty spike of voltage that will just zap capacitors. And if it gets through to the more sensitive components, it can destroy them. So there's parts of the circuitry that accounts for that momentary phenomena that occurs when you apply power. And one of the ways it was explained to me is they had a video of a high voltage transfer station getting put into service. Have you ever seen those videos where they flip this switch and this huge arc of plasma or whatever the lightning thing is arcs across until the two contacts come together?
No, I haven't seen that, but guess what I'm doing after this podcast?
There you go. But yeah, it's some ways to make a connection when you got 8 bazillion volts going through something with high current is once they get close enough, it will jump that air gap and create lightning until the gap is closed. And now you have a solid electrical connection in the metal and it's carrying the load. But it's a phenomena to see. And I'm thinking the person that was describing this was talking about relays. And with, when you're putting, say, 240 volts or 480 volts, not really high stuff, but stuff that knock you down if you were in the wrong place. And they say these relays are meant to be the two contacts are far enough apart that it won't jump it. And sometimes they even put dielectrics in between so that it makes it much more difficult for the voltage to jump the gap and basically spark and create intermittence, voltage powers, and all that other stuff. But we want to close those contacts. We want to make that connection. So as they get to a critical point, depending on the atmosphere at that particular time, the air and particulate and everything else in that area, humidity, it will jump that gap. You'll get a spark. Even very, very low voltage stuff. When you make a connection on a live circuit, it will spark. You might not see it, even low voltage stuff, but in these capacitor or these relays we're dealing with, you could actually see it and hear it. And so part of the design was to do it fast enough that that spark doesn't exist very long because it causes damage on the contacts. And I'm like, if that's the issue, and you're doing high voltage relays, basically, I'm thinking 480 volts, and you're opening and close these a lot of time, well, that failure mechanism is the damage that spark causes on those contacts to the point where they won't connect anymore, or they'll only spark. They won't make a good enough solid connection to avoid the sparking, which causes all kinds of spikes and problems in your circuitry. Or is it your computer and you turn it on and off? And that switch is a dome switch that can only go so many cycles before it fails. Or is it the electronics that's mitigating that inrush of circuit or current? Or is it a wear mechanism on a mechanical system that is wearing excessively or significantly with each cycle? I'm thinking of an unlubricated engine. I've often heard, I don't know whether it's true or not, is that when you start your car, it's the most stressful time for your engine, because then it's kicking combustion engines. It's kicking oil up into all the places it should be. Where if you go to the store and you make a bunch of stops and errands and stuff like that, the oil's kind of already where it should be. So that's one of many reasons why taxis tend to last a whole lot longer, because they're well lubricated more often. And I'm like, oh, okay. There's a lot to this question, but it all comes down to what are the mechanisms that you're worried about when it turns on or off?
Right. And the reality is you can't account for startups and shutdowns just through statistics alone, just through some, textbook off the shelf, through some magic equation. You got to understand it, and that might mean you need to test for it.
We should work. That might be cool. Let's come up with the mystical, magical. Just multiply it by 42, and you're good.
There you go.
Yeah, it always works. We won't tell you the units of it until you tell us a whole lot more information about what the mechanism is. But
right. But it's an interesting, it's a good question in that it's a conundrum, and I'm sure that this might be the first time our question asker has come across this scenario. And there's no harm in asking it, reaching out to see what you need to do. And I suppose the bad news, if there is that unfortunately, you need to delve into it a lot more than you perhaps were previously.
Well, I mentioned the inrush current for electronics, and connectors and relays and switches and stuff like that are involved in the start stop cycles, or turn on turn off type cycles. So I suspect part of it generically is to think of it as what parts of your system are involved with the change in transition from on to off, or whatever the cyclic nature of what you're talking about is. What sees that stuff and follow it through the electronics, through the mechanics, through everything else. And it might be a good exercise for an FMEA is, well, what happens in your system? What forces and stresses and phenomena occur unique to the cyclic nature versus its steady state nature? It's only that way that you're going to think through. It's not the only way, but it's a way to think through, well, what's different, what's happening that we need to be aware of so that we can understand it properly. The other part of this has been a longstanding, project on the wings kind of thing, is you need to understand the failure mechanisms. A capacitor sitting on a charge board doing its capacitive thing in the circuit is just a happy capacitor. It'll just drive all day long. But if you start pulling transients into it, which are common with turning on or turning off power, then it's not going to be so happy. That tends to break down the dielectric barriers that are key to say electrolytic capacitor. Yet for every component in your system, what is it that those phenomena, those stresses, how do they change, and then how they affect those particular components? And the same for mechanical. If I got a linkage, and every time I do a hard turn to the right, I'm thinking very old cars, the ones I used to be able to work on. There's metal on metal contact to make that motion occur. And how does that change versus very subtle light changes to the steering wheel? It's different. And that's, I think, the core of this message is that the phenomena in a cyclic nature, even if it's not excessive, is different than in a steady state. And I think was the genesis of this question. Well, how do I model this stuff? One of the parts of my answer to this, Chris, was that keep in mind that cycles is often used as a surrogate for time.
Yep.
So it's how many times does the braking system engage is different than how many miles the vehicle is driven. There's a rough correlation, but not perfect by any means. So that you see it with car or with tires. They say it's good for 50,000 miles or so many years. And they use two different time scales to deal with it. And so I think cyclic nature is also that way.
And the other thing that might blow people's minds is that if you have a startup which is immediately following another startup, that second immediately following startup might be much more damaging than just a run-of-the-mill startup.
Or vice versa.
Or might not add any damage at all because all the damage was done in the previous one. And now that it's sort of a bit of oil was splashed around where it needs to be splashed around, very fast secondary startup won't be that much of a deal. Yeah. So it's challenging to model to the extent that I wouldn't try it without trying to test it or at least understand what causes it to fail. The other thing too is that I suppose the question we throw back at our question asker is, well, if this thing's going to fail due to repeated startups and shutdowns, what will that failure look like versus a failure, full throttle open failure, so to speak? And if the answer is, well, I don't know what the difference is, well, that's the answer we need to give you right now. If you don't know, then we don't know what makes this different. All you know is it's just called startup and shutdown. You just don't know how that's going to stress or not stress the system in a different way. So if you don't know, then we don't know. So that without trying to be too adversarial or flippant, you really need to know what is going on when you start up and shut down. Until you do, you're not going to be able to find an easily accessible answer through Google, textbook standards, or random podcasts.
Well, there's I know I've used various simulation tools. Like electrical simulation tools have gotten better and better over the years, and where you can model the transients of the startup and take a look at, do I get an excessive voltage buildup? Is this component not ready to play the game in for so many milliseconds, but we're asking it to perform too soon? Do we need to put in some buffers or delays or other things in this so that the startup routine doesn't inadvertently damage our circuitry? And same for mechanical systems. You can use finite element analysis oftentimes to, here's a vehicle seeing a certain amount of vibration. That's great. We need to understand what types of sources are causing the vibration and those things, but we can also do it for startup. What's the amount of friction that it sees initially, or when this connecting rod slams into something? What kind of stresses and forces is it seeing versus when it's under normal operation? When what it's like trying to move a heavy object. It takes a whole lot of effort to get it started, but once it's going, assuming you got some kind of rollers under it, or it overcomes the inertia, that you can keep it going with less force. So using simulation tools and finite element analysis tools and other types of tools to model, how does the stress change? And I'm thinking, how does it change versus when it's just running normal?
But that simulation, I'd argue, proves my point, is that in that you said there was for example, the inrush currents is great simulation tools for inrush current. That's the mechanism, or that's the failure mode that you're worried about. So when I ask you what's how this thing fail, this electronic circuitry fail when you turn it on and off, well, one of them will be the one issue will be the effect that the inrush current has. Okay, cool.
No, it's not always inrush current. There's dozens of other phenomena that occur when you start an electronic box. So you got to think about all this stuff. But to your point, Chris, is, well, what exactly is it that's the problem here?
Right. So, but you can't just say, well, there's great simulation tools out there at the end. There's great simulation tools out there if you know what the failure mode or failure mechanism is. And even if it's a suite of failure modes or failure mechanisms, if inrush current is one of 20 or whatever the right number is, at least you're starting to think about what is different about turning it on and turning it off versus just leaving it on.
Yep.
And now you're starting to cook with gas when it comes to answering questions in more quantifiable ways. But if you don't know what the answer is, if you don't even have the equivalent of inrush currents as an answer ready to go, you're beyond statistical help.
Yep. Yeah. Well, I'm trying to answer the question, how do you know? And I know I did one test on a handheld device, and one of the use case concerns for the mechanical team in particular was that it's a handheld device and people are going to drop it. And so they were thinking, oh, we'll just do the 10 random drops from 3 feet. And if we pass that, we're good. We're like, no, not really. How about we figure out how it fails if we drop it in more of a Halt style approach to it. And like, well, we don't need to, that's a lot of testing and we don't know how to do this. So we hired a team that did finite element assessment for when something hits the ground. It's like it's being dropped from 3 feet or 4 feet, and would just use gravity. And this is inadvertent drop, not somebody's throwing it down. Turns out the failure mechanism was much different if somebody put a lot of effort into dropping it versus it just dropped. And we did a model, and it wasn't the mechanical system; it was the circuit board itself would flex in a way. In an unexpected way, and in the area of the highest bend was right under the crystal, and it would break the crystal inside the can. If you know what a crystal component looks like, sometimes, not always, but they're sometimes put in a small metal can, and there's a piece of crystal suspended between two trays that provided the electrical timing function for your circuit. And if the crystal breaks, it's a different frequency now, if it's still connected at all. And the electrical guy was like, I've never seen a crystal break before. It's in a metal can. It's all this stuff. That's not enough force to cause that to happen. And the simulation we did was purely mechanical. So we didn't have the model for inside the crystal. I said, well, let's go find out. So we put it on a vibration table and swept the vibration up. And sure enough, we were able to see the same load or vibration pattern in the circuit board that the simulation expected when it got hit, a shock kind of pulse into it. And the crystal immediately broke. And I wouldn't have believed it unless I'd seen it. So we went back with the evidence and said, here's the simulation, made us go look for, is that real or not? We simulated a shock on a vibration table that mimicked what a person dropping it from 3 feet onto concrete would do. And it broke right where we suspected it would. And both the mechanical guys and the electrical guys were just flabbergasted. And then we redesigned how that board was attached and how it absorbed that energy and transferred it. But it started from, we don't know what happens when you drop it. And that's, I think, a start-stop scenario where it's now in free fall versus a hard object and it stops falling. But the thinking was, well, what happens then? So let's go figure it out. And we did.
Well, that's the answer, is you got to start with trying to find out what makes the start-stop different to full throttle use.
Yeah. And just a short list of things. I'm thinking of the inrush current for electronic box. This is my favorite one because I had a bunch of issues with that. Shock. Just mechanical system goes from being happy dappy sitting there doing nothing to full on load, and that's a shock in some cases. What are some other types of forces that would likely occur at a start or a stop type behavior?
Well, it's not even just that. It's just that lubrication's a good one. It takes a little while for lubricants to go around. Ball bearings, another one. Ball bearings are designed to operate at certain temperatures ball bearings are designed to eliminate friction. And what they do is eliminate most friction, but not all. So there's always going to be residual amount of heat, and high quality ball bearings are designed in a way where they know the heat that's going to be generated. Then they can take into consideration the extent to which balls and races, etc., expand. And so every time you start and stop, you have ball bearing, or starting in particular, the ball bearing operates for a little while at a lower temperature, which it's not designed to operate at until
it gets up to speed.
Enough friction. Yeah. So that's another example.
Well, there's just the inertia, overcoming the initial inertia. While it might not be a hitting the floor kind of thing, it changes the dynamics of where the stresses are being applied across your ball bearings or across the shaft or across the linkage of some sort. Yeah, there's a lot of them out there. The summary is you got to start with, well, what's different? How do those differences and stresses affect your products? And that's a very tall order on most today's complex products. So start with what could go wrong. That's why I mentioned FMEA. Under a different set of scenario of what happens when we start this thing? What happens when we stop this thing? And where does all that energy go? Whether it's electrical or mechanical energy or even chemical energy. Where does it all go? How does it move from one state to another state? And is it smooth and gentle, or is it abrupt and damaging, or what? But yeah, there's a lot to unpack in this question. And then one last thought, Chris, and I'm surprised I didn't bring it up earlier. It was when he talked about excessive start-stops. One of the phenomena I run into in accelerated testing is that we try to accelerate it very, very fast because we don't have time. We don't want to run the tests for that long. We don't want to take up the lab for that long. All kinds of reasons we try to run our tests very fast. One of the problems with that is that you inadvertently invoke a failure mechanism that is not realistic to actually occur during nominal use. Even though it's a start-stop system, if I do it excessively, then I'll create a failure phenomena that just won't happen otherwise. The simple example is if I accelerate a system that has a polymer in it and I excessively heat it up to above its melting point, it's going to fail for a completely different reason than at nominal temperatures.
Right.
So it's doing excessive start-stops may cause phenomena to occur that is just unreasonable to expect in normal conditions. So there's invoking different failure mechanisms or accelerating phenomena that's just not the one you're looking for. Is be very careful with pushing systems with excessive cycles or forces or whatever, unless you understand that it will still behave the same as at nominal conditions for all the different things that are changed when you go at it very hard.
And it's not just melting. It's for those who've done material science, there's this thing called eutectics. It's that where things don't melt, but they change their characteristics. In fact, I'm doing a case study now on one of the courses I'm developing for Delta Flight 1288, where a tie rod hole in the hub of the compressor fan on an aircraft engine had a fatigue crack. Now, they worked out that the crack started from two ladder cracks or a couple of ladder cracks that are usually associated with drill bits going through holes and just scraping as they go.
Mm-hmm.
But they're able to work out, no, the drill bit actually didn't create holes. The drill bit actually, it had, when some titanium chips clogged up the coolant, things got really hot. And so they had these 2 or 3 sort of ladder regions of recrystallized titanium alloy, because for a couple of microseconds, they were heated to above 1200 degrees Celsius.
Wow.
And so their structure was fundamentally changed. And you had these 2 little shallow valleys of
different metal.
different metal, brittle, smaller grain sizes. And so the thing was perfectly smooth when it was machined and manufactured. But within, as soon as this thing was used for the first time, those little brittle valleys of material quickly failed. And so what was left behind were these ladder cracks, which then became the initiating point for fatigue cracks, which ultimately caused the hub of the engine to fail.
Oh, that's why you love reliability engineering. There's the world we work in and live in is always presenting all these cool new things, the way stuff can fail. Not so good for the people on that aircraft, but but the idea is that, you got to think it through, and you're always going to hear, well, that'll never happen. And, it's time and money and risk always involved. And if you're really, this is going to happen, go prove it. Do the simulation work, do a one-off test and see what is there, get halt going, see if that is one of the mechanisms that appears. Yet it's what changes is always a risk in any system, whether it's a mechanical, electrical, or human system. Something changes, something's likely to break. Be aware of that and think it through. Hopefully we gave you a bit of food for thought, and thanks for the question. Let's see, was it signed? Alfredo sent it over. Pretty broad question, probably deserves more than 1 or 2 podcasts here, but we'll hopefully got an answer back to him, and I'll point to the podcast when it comes out for him. So thanks a lot, Chris, for helping me get this through. And let's see if we get a question or 2 to follow up. Add a little specificity for us as best you can to help us answer it more cleanly for you. Head over to accendoreliability.com/go/SOR. A couple of ways to get in touch with us. Chris and I and the other hosts are available through LinkedIn and our About pages. Lots of ways for you to get a comment or question over to us, and we really do look forward to those. Jeez. I'm afraid now to push the end recording button. It's a stopping function. I don't know what'll happen.
That's right. Yeah. So like us, we take a bit of while to warm up and cool down after each podcast.
There you go. All right. Thanks much, Chris. Talk to you soon.
Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.